Hi class, Mrs. Brummel here. We're going to be getting into 4.2 with related rates problems. So these are some classic calculus type problems. And this is basically just being able to apply all the different things we've learned about a derivative to some contextual problems. Okay, so here's kind of some steps. These are laid out for you by your book. But basically, make sure we know what we're finding. So read the problem carefully. Definitely draw a picture if you can. Identify what your variables are and assign symbols to them. Label your picture. Identify rates of change will always be your derivatives. That's really important. Be sure to list units for our variables and indicate what is given and what is asked for. Okay. We're going to write an equation that relates our variables, and it may be necessary to use more than one equation. We're going to differentiate both sides of our equations, and we're going to substitute in the numerical values we know and then solve for our unknown rate of change. Okay, so that's a lot. We're going to refer back to that as we go through this question. Okay, here we have this first one. A golfer hits a ball into a pond, causing a circular ripple. If the radius of a circle increases at a constant rate of 0.5 meters per second, how fast is the area of the circle increasing when the radius of the ripple is 2 meters? Okay, guys, so basically we are talking about a circle. And we are relating kind of two different things here. We have the area and we have radius. Well, we have an equation already dealing with a circle that deals with the area and the radius. The area of a circle is pi r squared. So we already know that based on what we know about a circle. Okay, so as soon as I take the derivative here of both sides, you guys, well, actually, before I do that, okay, so we have the radius of the circle is increasing at a constant rate. So anytime I'm given a rate of change, that is a derivative. So they're giving me a derivative of r with respect to time. So dr dt is 0.5 meters per second. How fast is the area? So again, they're looking for a rate increasing when the radius of the ripple is 2. So we are looking for dA dt, the rate of the area compared to time. So that's what we are looking for. And then we're given an instant. We're given that r is equal to 2 meters. Okay, so first, because we're dealing with rates of change, I'm going to go ahead and differentiate this equation. So we're going to take the derivative of both sides. So the derivative of a with respect to time is dA dt. Pi is just a constant multiple, so we're going to bring down our 2 and multiply by pi. Derivative here of r with respect to time is dr dt. So this would be the equation differentiated. Okay, so now we're going to substitute in the values we know. We know dr dt is 0.5. So we got 2 pi. We know dr dt is 0.5, and r this instant is 2. So we're going to put in 2 and 0.5. When I multiply all that out, I get 2 pi, and this is a rate in the area. So dA dt, area is measured in square units, okay? So we have meters, so this is going to be square meters. And then our unit of time, because this is a rate, is seconds. Okay, so our area is increasing at a rate of 2 pi meters squared per second when the radius is 2 meters, okay? I'm actually going to add that sentence, you guys, just so, again, we're practicing that interpreting part. So when the radius of the ripple is 2 meters, so that's our instant, the area of the circle is increasing because it's positive, so our area is increasing at a rate of 2 pi meters squared per second. So there's our rate and there's our unit. Okay, this guy. We have a revolving light located 5 kilometers from a straight shoreline. turns at a constant angular speed of 3 radians per minute. With what speed is the spot of light moving along the shore when the beam makes an angle of 60 degrees with the shoreline? So we already kind of have a picture here, you guys, to help us out. And basically, again, we need to kind of create an equation that we're going to differentiate, but we need to look at what we know already. So we have a constant angular speed. Constant angular speed here, okay, I'm going to call it d theta dt. So angles are often measured in theta, so I'm going to call the rate of our angle, or our angular speed, as a rate. That's going to be 3. So that's this piece, okay? Okay, 5 kilometers is a fixed distance. Come back to that. With what speed is the spot of light moving along the shore when the beam makes an angle of 60 degrees? So they're asking the speed that the light is moving along the shore. So that's going to be with respect to x. So we're looking for dx dt. Okay, so basically now, you guys, I need an equation that relates theta and x. So if I go back to my right triangle, okay, we have our angle theta, and we have x, and we have 5. So we have some right triangle trig ratios. I could say the tangent of theta is equal to opposite over adjacent, which for me is this. And I'm actually going to multiply both sides by 5 and just say that x is equal to 5 times the tangent of theta. Okay, so now I need some things in terms of rates and times. So I'm going to go ahead and differentiate each side of this equation. So the derivative of x with respect to time is dx dt. Okay, 5 is just a common multiple, so I'm going to leave that there. Derivative of tangent is secant squared, and then times d theta dt. All right, so let's plug in what we know. Okay, so there, again, if you guys look at this picture, this is 60 degrees, but this is the, that revolving light is out here. So this angle, right, is 30 degrees when this one is 60, right, in a 30, 60, 90. So that's the angle I'm going to use here. So we are looking for dx dt. 5 times secant squared, if I could spell secant, there we go, secant, and I'm actually going to write it like this, you guys. And I'm going to say also, because this is in terms of radians, I'm going to do 30 degrees in radians. So 30 degrees as a radian angle is pi over 6. So I'm going to go ahead and put this in as pi over 6 squared. And then d theta dt for us is 3. All right, so remember secant is the same as 1 over sine. So I could also write this as 5 times 3 is 15. And then cosine of pi over 6 squared. Okay, so what is cosine of pi over 6? Cosine of pi over 6 is 3 over 2. So we got 15 over 3 over 2 squared, which is going to be 15 over 3/4. Flip and multiply, and I end up with 60 over 3, which is 20. Okay, so our dx dt is 20. Okay, so what is this? This is a rate at which the light is moving along the shoreline. So this is going to have to do with a distance per time. So our distance was kilometers, and our time here we have was minutes. Okay, again, I am going to write a sentence here to help us out with that. Okay, so when we're going to say when the beam makes an angle of 60 degrees with the shoreline. So I'm kind of using that last sentence to kind of help my sentence starter. So we're talking about that instant, okay? When the beam makes an angle of 60 degrees with the shoreline, the spot of light is moving along the shore at a rate of 20 kilometers per minute. Okay, so again, we gave the context there, we gave the exact instant, and then we gave the rate with proper units. Okay, example 3. Okay, a person standing at the end of a pier is docking a boat, pulling a rope at a rate of 2 meters per second. The end of the rope is 3 meters above water level. How fast is the boat approaching the base of the pier when 5 meters of rope are left pulling? We're assuming the rope never sags and the rope is attached to the boat at water level. So here again, we kind of have a picture showing us what's happening. Okay, so again, I can kind of see I have a right triangle here. And so I'm going to write an equation that incorporates all these things. Okay, so some variables I have are, I have x and L. So what are those representing? So x is like the horizontal distance, L is the rope, right? And as I pull in the rope, there's less and less rope that's going to be out. Okay, so we are looking for how fast is the boat approaching the base of the pier. So we are looking for dx dt. That's what we're looking for. Okay, dl dt is the rate that the rope is being pulled in. dl dt. And this is being pulled in at a rate of 2 meters per second. Now, actually, this is going to be a negative rate because the rope is decreasing in length, right? As we pull the rope in, there's going to be less and less rope out, okay? All right, so that's why it's negative. All right, so now we are going to, again, write an equation that puts all those three, okay? So the other thing that we know is we know dl dt, we know that this is a fixed rate, and I can, again, kind of see I have a right triangle here. So something that relates all three sides is the Pythagorean theorem. So I'm going to say 3 squared plus x squared equals L squared. I went ahead and put 3 in right now, you guys, because I don't have any rate at which this is changing, so I'm not going to need like a dy dt or anything like that. This is fixed. So I'm just going to put it in right now, because when I take the derivative of this function, that's just going to go to 0, which is great because I don't have anything that I need to worry about with a rate. So this is going to turn into 2x dx dt equals 2L dl dt. Now we're going to plug in what we know. Okay, so, and I'll write 0 plus so you can see where that went. Okay, so I'm going to plug in what we know. So we are asking how fast is the boat approaching when 5 meters of rope are left pulling. So this is our L. 5 meters at this instant, okay? And they're asking what is x? Okay, so wait a second. I have two things I don't know. I don't know dx dt and I don't know x. Well, actually, you guys, we do know a few more things. We know that when L is 5, so I'm actually going to kind of do a sidebar here. So we have 3 squared plus x squared equals, at this instant, we want L to be 5. Well, I could actually solve this using Pythagorean theorem, or I might recognize that's Pythagorean triple, 3, 4, 5. So when this is 3 and L is 5, x has to be 4. So the instant we're going to use, I'm going to put in 4 here as well. So we've got 2 times 4, dx dt is what we're looking for. 2L, L at this instant is 5, dl dt is -2. Okay, and then I'm going to do some solving. So we've got here, what do we got? -20. And then we're going to divide by 8. Okay, and when I do that, I get -2.5. And again, I need a rate. So this is in the rate at which the boat is approaching. It's negative because it's going closer and closer. That distance is decreasing. So this is in meters per second. Okay, so our rates, dx dt is -2.5 meters per second. Okay, last example here, guys. We have a container in the form of a right circular cone that has a radius of 7 meters and a height of 22. Here's a picture to kind of go with it. Okay, if water is poured into the container at a constant rate of 24 cubic meters per minute, how fast is the water level rising when the water is 11 meters deep? Okay, so this unit, you guys, anytime you see cubic, that is volume. Cubic units is volume, square units is area. So this is a rate that the volume is increasing, and so that is the dV dt, volume according to time. So this is going to be 24. Okay, so what else we know? We know our radius. I'm actually going to use r and h. That's kind of what the formula typically does. So our radius is 7, our height, or our b, is 22. Okay, so we're talking about volume, so I'm going to think about what is the volume formula for a cone. And volume formula for a cone is 1/3 pi r squared times the height. Okay, now, one thing that's helpful here, you guys, so what am I looking for? I'm looking for how fast is the water level rising. So this is going to be the height. So we are looking for what is dH dt. Okay, so if you notice, I don't have any dr dt information over here, and I'm not looking for dr dt. So it would actually be nice if I did not have an r in my equation, so that when I differentiate, I only deal with these two rates. Okay, well, how do we do that? Well, right now, we have a relationship between the radius and the height. If we were to divide the radius by the height, right now, that's 7/22, or I can also think about that if I multiply both sides by h, r is equal to 7/22 times h. So that's kind of the ratio in which I have to keep for this cone to maintain all the properties that it currently has. So I'm going to substitute this in for h, okay? And so I'm going to get volume is 1/3 pi r squared, or excuse me, not in for h, I'm subbing it in for r, because we just solved for r. Okay, so we're going to get 7/22 h squared times h. Okay, so if I square everything in there, we get the volume. So I'm going to square everything, and I'm going to multiply by 1/3. So I'm going to get 49 pi over 1452, so that's 22 squared times 3, and then h squared times h is h cubed. Okay, so now this becomes also easier to differentiate. We have less variables. This is a constant multiple, so we get dV dt equals 49 pi over 1452, if I can multiply, times 3h squared. When I multiplied by 3, this actually divides nicely by 3, you guys, so this is going to turn into dV dt equals 49 pi, oh, and I forgot my dH dt, okay, equals 49 pi over 484, h squared dH dt. Okay, so here's my function. Now let's plug in the things we know. So we know dV dt is 24. We know this, we're going to keep 49 pi over 484. H, at this instant, it is 22. Oh, I'm sorry. H, that's our instant we're looking at. H, at this instant, is 11 meters. And then squared times dH dt, that's what we are looking for. So we're trying to solve for dH dt. Okay, when I square 11, I get 121 times 49, so we're going to get 24 is 5,929.29 pi over 484 times dH dt. Okay, so when I divide 24 by this, we get dH dt is approximately 0.624 meters per minute. Okay, I'm going to add a sentence here. Okay, when the water level is 11 meters deep. So that's our instance. The rate, or we can say the water level, is rising, and again it's positive, rising, those kind of correlate. It's rising at a rate of approximately 0.624 meters per minute. Okay, that's everything for this video, guys. Thanks for watching.